Yeah, let me quickly remind you of the definition of the metric space we have studied the last time. Yeah, for a matrix space, we must first of all have a set X. And we must also have a function D defined on the cross product of the set X with itself. And its real valued, and then that must be a non-negative real valued function. Okay, the function D is a function from the Cartesian product of the set X with itself to the non-negative real numbers. Then we say that the set X and the function D is a metric space if the following three conditions are satisfied. The first condition is distance between D, where D is called the distance function, the metric or a distance function. And the first condition is metric, the distance between X and Y is equal to 0, must be equivalent to two elements, and X and Y are identical. And secondly, distance between X and itself must be definitely 0. No, sorry, that's the second condition must be the commutative property. Okay, the distance between X and Y must be same as distance between Y and X. And the last condition is the triangle inequality, called the triangle inequality, which is the distance between X and Z must be less than or equal to distance between X and Y plus distance between Y and Z. That's so-called the triangle inequality. So we say that the set X with this metric distance function D is a metric space if the function D satisfies all those three rigorous conditions. Yeah. And what were good examples of the metric space we have justified last time? First of all, if the set X is the whole real number line and the distance D on the whole, between the two real numbers X and Y is defined by absolute value of X minus Y. Right? Then, this set, the set of all real numbers X and the distance function D is an example of a metric space. We can easily figure out that this absolute valued function satisfied all those three rigorous conditions. That's easy for you. Right? And secondly, we have studied a lot about what? This absolute value metric, okay, on the whole real number line in the real analysis, real analysis 1 and 2, right? We did, study, a lot of stuff in the absolute value metric already, right? Open set, closed set, continuity, uniform continuity, and so on, right? Yeah. So in this is so-called user metric. User metric on the real number line, okay? And on this user metric on the real number line, we already studied a lot of stuff on. Okay. And then let's do a little bit generalization of this user metric to arbitrary n-dimensional Euclidean space Rn. And then distance between two elements in Rn is defined by the square root of sum of squares. Okay, that's a square root of sum of squares of components of the two vectors X and Y in the n-dimensional Euclidean space. And then this n-dimensional Euclidean space Rn and the distance function d will be another example. Of the metric space. If n is equal to 1, this distance metric in Rn is reduced to what? The usual metric on the real number line R, absolute value thing, right? If n is equal to 1, what is happened? That's one-dimensional thing, and then what? Yeah, so that's summation from 1 to 1, okay? Square root of summation from 1 to 1, square sum of components. So then that is exactly reduced to what? One-dimensional absolute metric, you know? Okay. So in the previous example. So those two are examples on the Euclidean space, the Euclidean metric. Those are examples of Euclidean metric. We have, okay, justified last time, and the proof of the second one. I am sorry, but that was quite messy, so then I sent out the kind of well-organized proof. I uploaded that well-organized proof of that, Rn second example on the web, on the Learning Hub for you. So those are Euclidean metrics, examples of Euclidean metrics. How about the non-Euclidean metrics? That's what we want to start with today. Example number 3. What is a good example of non-Euclidean metric? Let's let the set X be the collection of all continuous functions, real valued continuous functions, defined on a closed bounded interval from A to B on the real number line. That's the standard notation of what? This is the standard notation of the collection of all continuous function f defined on the closed bounded interval from A to B on the real number line. Yeah, this is our set X. And let's let D be defined on the Cartesian product of the set X with itself, and it is, let's let D be the function from the Cartesian product of this set X with itself to the non-negative real number be such that, let's let the function D, which is defined on here, which is negative real value, to be such that D function value at two functions f and g, f comma g, that is an element, arbitrary element in the Cartesian product of this set X with itself. Let's let D at fg be defined by the supremum of absolute value of the two function values. Where X is in the domain interval from A to B on the real number line. So D is a function. This definition for D is a function from the Cartesian product of what? This set X with itself to the non-negative real numbers, right? This is non-negative because this is a supremum of absolute value thing. Then what is the geometrical interpretation of this definition? The metric, the distance between the two continuous functions f and g defined on a closed bounded interval. And here is the domain interval from A to B on the real number line R. And then on that closed bounded interval from A to B, there are two continuous functions f and g. There are two continuous functions f and g, for example, defined on the closed bounded interval from A to B on the real number line R. And both are continuous functions. Both are in this set X, defined on a closed bounded interval from A to B. And then how do we define the distance between those two functions f and g? D function here. Okay? you know, for each x on the domain interval, okay, there is what? The pointwise distance between f and g, right? Which is absolute value of a difference of fn, fx, and gx, right? Yeah, it is defined pointwisely for every x on the domain interval. For the x over here, yeah, this is the difference, pointwise difference between f and g function at the point x. If you choose another x on the domain interval and then at that another x, there is another pointwise distance between f and g functions. Then there are a lot of pointwise difference between f and g functions, and then take the supremum of all of them there. Take the supremum of all of them there. Then on this picture here, where does it happen? It's roughly happened over here, I believe. So this distance is the d function, the metric d of the two functions f and g, which is the supremum of pointwise distance between f and g functions, okay? Geometrically. If we fix a x on the domain interval, and then at that each fixed x, there is what? Pointwise distance between two functions f and g. Here it is. And there are a bunch of them depending on x, right? And then take the supremum, the maximum of everything there. Take the supremum of the distance, pointwise distances. And that's how we defined the distance between the two continuous functions f and g defined, okay? F and g on our set x there. Then we claim that this set x with this metric function d is a metric space. That's what you want to claim. So that will be a non-Euclidean example of metric space. Okay, non-Euclidean metric space. That's an example of non-Euclidean metric space. How do we start the proof of it? The justification of it? First of all, is the function d well defined? That's what you have to check out, first of all. What I mean is the d function from here to non-negative real numbers? Are you sure about it? Of course it's non-negative because the absolute value sign there, right? But is it a finite value? In other words, does this set have the supremum value, which must be finite? Maybe or may not be in general, right? Then how do you guarantee this pointwise, the collection of pointwise distance between f and g is bounded above? Which means what? How do you guarantee this collection has its supremum? How do you guarantee that, first of all? What I mean is, first of all, our d function must be well defined. What I mean is, d function must be what? Non-negative real valued function. How do you guarantee this? Why don't you remind you of the stuff we have studied in the real analysis? What was the very nice property of continuous function defined on a closed bounded interval? We have studied in real analysis. Huh? Why? What was the name of the theorem that did guarantee the boundedness of this pointwise distance set? You remember the maximum minimum theorem. Do you remember that? Maximum minimum theorem for a continuous function defined on a closed bounded interval, right? Yeah. We take two arbitrary functions f and g in our subset in our set X. Then, since the f minus g function, the difference between two functions f and g, f minus g, defined on a, let me try to describe them a little bit more precisely. And since the difference between two functions f and g is continuous, on a closed bounded interval from A to B by the maximum minimum theorem. Okay, the maximum minimum theorem we have studied in calculus 1, I think. Sorry, not the real analysis 1. The collection of, more precisely, actually absolute value of f minus g. Absolute. Since absolute value of f minus g function, absolute value of f minus g function is continuous on a closed bounded interval from A to B by the maximum minimum theorem, its image set, which is this, right? Its image set. Its image set has the maximum and minimum value. Actually, more precisely over here, has the maximum value. Okay? Maximum value. And so what? Yeah, this pointwise distance collections has what? Has the maximum value, which means the supremum value. So what? That means what? That means the supremum value must be finite, some finite number. Okay? This pointwise distance set has the maximum value, which means the supremum of this what? The collection of this pointwise distance set must be some finite real number. Bounded above, that's what that means, because this pointwise distance set has the maximum. So this pointwise distance set is bounded above, which means what? Which means the by what? By the supremum property. Okay? Bounded above set has the maximum, has the supremum value. Right? Yeah. Which means this image set of f minus g function is bounded above and so by the supremum property. By the supremum property. We have studied at the very beginning of the real analysis 1. The supremum of that image set exists. Now, what was the supremum property we have studied at the very beginning of real analysis 1? Every bounded above set has the supremum value. That was the supremum property. We have studied at the very beginning of the real analysis 1, which means the distance between f and g we have defined there, which is the supremum. Okay, supremum of the pointwise distance values on the whole domain interval from A to B, okay, is some finite number. This supremum value exists, then that means what? This whole thing is a finite, supremum of this set is a finite number, and which is, of course, non-negative because of the absolute value sign. So we guaranteed that the D function is well defined. The function D we have defined there is well defined. It is well defined, not ill-defined. That's well defined. So our function d is really a function from here to non-negative real number. Okay? Yeah. And then we can easily check the three rigorous conditions for d function, right? That's easy for you. Distance between the two functions f and g is equal to 0 is equivalently what? That's equivalently, by the definition of the function, supremum of pointwise distances on the whole domain interval is equal to 0 by the definition of the function. Then that's equivalently what? Supremum of this set is 0. And then each value on here is non-negative. Then what should it be equivalent to? Supremum of all those non-negative values is 0. Then what? What must be? This must be equivalent to what? Each pointwise distance must be 0. There is no other choice, right? So equivalently, each pointwise distance between f and g must be 0 for all x in the domain interval from a to b. Then that's equivalent to what? Which was what we have desired. Okay? Now all pointwise distance between f and g is 0 for every x on the whole real number on its domain interval from a to b. That's equivalently to what? Then there is no other choice. Okay? The all pointwise values for f and g must be identical. That's what then equivalently. Then finally, that's also equivalent to what? What is that statement for? That statement is for what? The identicality of two functions f and g. F and g must be identical. F and g must be the same functions on the domain interval from a to b equivalently, which was what we have desired to check the first condition there. First condition. Yeah, distance between f and g is equal to 0 is equivalent to what? Two functions f and g are identical. That's exactly the first condition to be a metric space. Yeah. The second condition is trivially true because what? Absolute value is commutative. Distance between two functions f and g. By the definition of d, that is again the supremum of all pointwise distances between f and g functions. But absolute value of f of x minus g of x is what? Same as absolute value of g of x minus f of x. Because absolute value is commutative, right? Then what? How do we rewrite it? Supremum of what? Supremum of pointwise distances between g and f functions on the whole domain interval from x, a to b. Then by the definition of d, again, that will be exactly what? Distance between g and f. Okay? Yeah, this is true for all f and g in our capital X, set capital X. So which means the distance d function we have defined is commutative. D at f and g is same as d at g and f for every f and g in x. That's exactly the second condition. How about the last condition? Triangle inequality. So let's let three functions f and g and h, f, g, and h be in our set X, or three of them are continuous functions defined on a closed bounded interval from a to b in the set X. And then distance between f and h. What has happened to the distance between f and h? By the definition of d function, again, that is the supremum of pointwise distance between f and h functions. On the whole domain interval from A to B. Right? And before we take the supremum, what I mean is before we apply the definition of D function, let's look at the absolute value thing first. You already know absolute value things is what? The absolute value thing has what? The triangle inequalities. Right? So then let's describe. What happens, the distance, pointwise distance between f and h functions at any point x on the domain interval from A to B. That is, by the triangle inequality for absolute values, we have already studied in the real analysis, that is less than or equal to sum of pointwise distance between f and g functions and pointwise distance between g and h functions. Then what happens on the next line? That's one of the pointwise distances between f and g functions at any fixed x. So then that pointwise distance must be less than or equal to what? The supremum of all pointwise distances between f and g functions. Because that's a supremum, right? Same thing for the next absolute value sign. Okay? So that's one of the pointwise distances between g and h functions at the fixed point x. So that must be, of course, what? Less than or equal to the supremum of the pointwise distances between g and h functions. Right? That is happening there. But by the definition of D function, this first supremum over here is same as distance between f and g functions plus, by the definition of D function again, this second supremum over here is, that means the distance between g and h functions. So absolute value, okay? This pointwise distance, this is the pointwise distance between f and h functions at any fixed point x is less than or equal to the sum of those two distance functions. Distance function between f and g plus distance function between g and h. This is true for all x, this inequality. This inequality is true for all x on the domain interval from A to B. For any point x in the domain interval from A to B, the pointwise distance between f and h at the point x is less than or equal to this fixed real number there. That's distance, a sum of distance between f and g and then distance between g and h. Because this inequality is true for every x, what do you conclude? That concludes that distance between f and h, which is by the definition of D again, the D function again, supremum of the pointwise distances between f and h. Must be less than or equal to the right hand side. Because this inequality is true for every x on the domain interval. Yeah, no matter what point x on the domain interval we choose, this pointwise distance between f and h is less than or equal to this fixed real number. So the supremum of all of them must be also less than or equal to. What I mean is this fixed real number is an upper bound of what? Upper bound of all those pointwise distances between f and h functions. So their least upper bound, which is their supremum, must be less than or equal to this regular upper bound number. That's what that means. This is true for all. For all f, g, and h, we have set up at the beginning there. So that proves the last condition of the metric space there. So this set x with this function d, it makes the metric space. Okay? And d is a well-defined functions defined from the Cartesian product of the set x with itself to the non-negative real number. That's well defined, first of all. And then the d metric function d, distance function d, satisfies all those three conditions now, rigorous three conditions there. So this set x with this distance function d makes a metric space. And that's an example of non-Euclidean metric space. Non-Euclidean metric space. Non-Euclidean metric space. Any questions or any comments? Then what's the next stage then? How do you define an open closed set on this kind of general metric space? Our definitions for open and closed sets on this general metric space will be reduced to open and closed sets on this one-dimensional Euclidean space we have already studied in studied in real analysis. Okay? So what I mean is, this user metric on the whole real number line will be just one simple example of the general metric space setting we currently study in this class. Then how do we generally define open and closed sets in this general metric space? Whose special case will be the open and closed sets in this user metric space on the whole real number line we have already studied in the real analysis then. Instead of absolute value thing in the user metric, we use what? This d function we have defined in the general metric space. That's the only difference. And you can easily draw some geometrical picture, imaginational picture for yourself. Definition. Okay? Definition. We have a definition, first definition. We have a metric space X and D. X is a set, D is a metric. Okay? And let's let X not be an element in the whole metric space X. And let's let R be a fixed real number, fixed positive real number. Then we define the open ball. We define the open ball with radius R centered at the point x naught, which is denoted by capital B at x naught comma R. That's the standard notation. This is the standard notation of the open ball with radius r centered at x naught. This is defined by the collection of all y's in the metric space X such that the function value between x and y is less than r. The function value at x naught and y is less than r. That's the formal definition. This is the formal definition. This is the formal definition of the open ball with radius r centered at the point x naught in the metric space. And you can easily draw some geometrical imagination picture for yourself. Yeah, here is, I don't know, how the whole metric space X looks like. Okay, if the metric space X is the set of the whole real number line R, then that looks like this, right? But I don't know how it really looks like. Or the metric space X may be the two-dimensional Euclidean space, or three-dimensional, four-dimensional, etc., right? What I mean is the metric space maybe some Euclidean metric space, or the Euclidean, the metric space X, maybe even somewhat non-Euclidean metric space we have just studied. And I don't know how the metric space X looks like. It depends. And then we have a point x naught in the metric space. And then how do we define the open ball with radius r centered at the point x naught, which is fixed on the metric space? That's the collection of all y's in the metric space, in the same metric space. The collection of all y's. The collection of all y's. Collection of all y's in the same metric space X, whose distance from x naught is less than r. Whose distance from x naught is less than r, right? Then you can imagine this kind of what? Open ball with radius r centered at x naught on the metric space, right? Well, actually, don't trust my picture here too much, because what? Depending on how the metric space X with the function metric D looks like, this definition of open ball may look different, right? Well, actually, if our metric space X is the whole real number line R, the usual metric, then how does that open ball looks like? That's exactly what? Open interval from x naught minus r to x naught plus r, you have already experienced in the real analysis, right? But how about if our metric space is the two-dimensional Euclidean space, and we have x naught in the two-dimensional Euclidean space? That is our metric space X. Then how does this open ball with radius r around that point x naught looks like? That will be exactly this open ball thing, right? Open ball. The collection of all y's in the second two-dimensional metric space whose distance from x naught is less than r, right? That's exactly the open ball. Okay, open ball with radius r centered at x naught. That's how it looks like, right? How about in the three-dimensional? Yeah, in the actual two-dimensional, that's more precisely, that's a what? Open circle. But in the three-dimensional, there will be an open ball, three-dimensional ball around, right? Yeah. So depending on how the metric space looks like, depending on how the metric D is defined, we may have different shapes of what? Open ball defined there. But our imaginational picture, for easy imagination, we mostly use what? The open ball picture here, right? For easy imagination. But, it may not be articulate. It may not be precise, okay? Depending on how the metric space is defined. Okay? Yeah. How about in this example of non-Euclidean metric space? We have just finished to justify. Okay? We have a continuous function f defined on the closed bounded interval from A to B. And this function f is an element in the metric space X, which was defined by C at closed bounded interval from A to B, right? And then let's let R be an arbitrary positive number. And then how does the open ball with radius R centered at this value, this element f, looks like in this non-Euclidean metric space? How does it look like? You know what I'm doing, right? Subtract R and add R to each pointwise f value on the whole domain interval. And then what? How does that open ball with radius R centered at this function f looks like? That will be the collection of any continuous function between those two dotted curves, right? You imagine that, right? Yeah, that's how this open ball looks like on this kind of non-Euclidean metric space. You can imagine, right? Yeah. Yeah, there are a bunch of infinitely many, uncountable many continuous functions, right? Defined between A and B domain interval, between those two dotted curves, right? As far as you can take any other continuous functions defined on the closed bounded interval from A to B on this dotted curve, between those two dotted curves, that will be what? That will be one of the elements in this open ball with radius R centered at the function f. Right? That's how it looks like. That's how this open ball looks like on this kind of non-Euclidean metric space. So depending on how the metric space is defined, our ball may look different. Yeah. Then let's use this open ball definition to define an arbitrary open set on the metric space. On this matrix space again, general setting of matrix space again, let's let capital O be a subset on the whole metric space X. Then we say that the subset O is open. How do you define the openness of this subset O in the general matrix X, the general matrix space X? We say that the subset O in that general matrix X is open if no matter what point X in that subset O you choose, depending on that, there is some positive real number R. There is some positive real number R such that the open ball with radius R around the point X is what? This whole open ball with radius R centered X is still a subset of the subset X. Subset O. That's the formal definition of the openness of a subset O on the metric space X. And then if you reduce that to Euclidean metric, actually the user metric example with absolute value thing, and then that will be exactly what we have studied in the real analysis, right? In the real analysis, you can easily recognize. Yeah, here is some metric space X. I don't know how it looks like. And there is some open subset O. There is some subset O in the whole metric space X. And then when do we say that this subset O is open? We say that this subset O is open if no matter what point X you choose on the subset O, depending on that, there is some open ball around it. There is some open ball around it which is still what? In the subset O itself. Right? That's the formal definition of the openness of the subset O in the general matrix space X. But if you let X be the whole real number line R with what? If you let D be what? If you let D be our user metric, and then what? this openness definition is exactly reduced to what? The openness definition on the real number line R we have already studied in the real analysis in the last year. So that's exactly the generalization of it. Generalization of it. Yeah. Any questions or any comments on it? So whenever we describe the general setting in the general metric space here, then you can always try to imagine the specific examples of this, the general setting, which is what? Which is what's happened on what? The user metric we have studied in real analysis. Then they are exactly matching. They are exactly matching. Then what is our very first lemma about the open set? Of course, this open ball is an open set. Any open ball is an open set. In the user metric space on the whole real number line R, this lemma is reduced to what? Every open interval is an open set, right? Yeah. That's what that means in the user metric, in the whole real number line R, we have studied in the real analysis. Then how do we justify the openness of any arbitrary open ball in the general matrix space X, which I don't know. I don't know how it looks like, right? And then here is some point X naught, and there is some open ball with radius R around X naught. I don't even know how, if the open ball really looks like this kind of a ball, I don't know. That's for our easy imagination. Then how do you prove this open ball with radius R around X naught is open? Using the definition of open set here, down here. So to prove the openness of this open ball, let's take an arbitrary element X in that open ball. And then, choose any point X in the open ball there. Then we should prove another smaller open ball around X is still sitting in what? The larger original open ball around X naught, right? That's what we must prove. Then what is your right choice of the radius R around point X? Then the smaller ball around X must be still sitting inside the larger open ball, original open ball there. Then because the point X we have chosen is arbitrary on that original open ball, it claims what? The openness of our original open ball, which was what we have desired there, right? Then what is your candidate for radius around X? Let's let S be, where S will be the radius of the open ball around the X here, which is still sitting inside the original open ball around X naught. Then what is your choice candidate of the radius S around X? How about whole R distance minus distance between X and X naught? So let's let S be the difference of original radius R and distance between X and X naught. I believe that will be a good candidate for the radius around X of the open ball, which must be sitting inside the original open ball there. Then we claim open ball with radius S, open ball with radius S around the point X is still sitting inside the original open ball with radius R around X naught. That's what we must claim. We claim. Okay. Using what? Using the triangle inequality, I guess. Yeah, using the triangle inequality. This claim is easily proved. Okay, easily proved, and then we will start from this point next time.